שלום, ברוכים הבאים לטקס הענקת פרס על שם מנחם שרגא ותיאודור דיקר. מלחמת ששת הימים התחוללה לפני כ-56 שנה. במלחמה זו נפלו שני תלמידים של המחלקה לגיאולוגיה, מנחם שרגא, זיכרונו לברכה, היה בן 27 בנופלו ביומה הראשון של המלחמה ב5 ביוני 1967. הוא היה לוחם בחטיבה ירושלמית. אחותו של מנחם, אלה, נמצאת איתנו היום, ואנחנו מודים לה על זה שהיא ממשיכה את המסורת החשובה. מנחם וטדי סיימו את הלימודים, את לימודי מוסמך במחלקה לגיאולוגיה. עבודת המוסמך של טדי דיקר עסקה בבזלות ודייקים של גבעת המורה. העבודה הזו הייתה עבודה חלוצית שהיוותה בסיס חשוב לעבודות דוקטור ומוסמך נוספות. מחקר הדוקטורט של טדי, אותו התחיל אך לא זכה לסיים, עסק בהידרולוגיה ובגיאוכימיה של מי תהום. זהו תחום מחקר מרכזי במכון למדעי כדור הארץ עד היום. מנחם שרגא סיים את לימודי המוסמך בגיאולוגיה בהצטיינות, בעבודת המוסמך שלו מנחם חקר את מינרליזציה ברזילית באזור הפרן. נושא זה נחקר גם מאוחר יותר במכוננו תוך התבססות על עבודת השדה המצוינת שבוצע על ידי מנחם. הקהל מתבקש לעמוד לדקת דומייה לזכרם של טדי דיקר ומנחם שרגא. נא לשבת. ככל שנה, כמו בכל שנה, אנחנו מעניקים היום את הפרס על שם טדי דיקר ומנחם שרגא לתלמידי מחקר מצוינים. ועדת הפרס בחנה את המועמדים ובחרה כחתן הפרס לשנת תשפ"ג את הסטודנט שי אביר מהנימוקים הבאים. המחקר של שי אביר מתמודד עם השאלה מה קובע את טמפרטורת המים בריף האלמוגים באזורים גאו-אקלימיים שונים, תוך התייחסות למקרים של הלבנת האלמוגים כתוצאה מגלי חום. שי בחן את הנושא במסגרת עיקרון שימור האנרגיה והתבסס על מדידות ישירות של הרכיבים העיקריים של שטפי חום בשיטת אדי קובריאנס. שי מצא שבסביבה המדברית אידוי לאוויר היבש מקרר את המים וכך טמפרטורת המים נמוכה יחסית, וגלי חום ימים חולפים מהר באופן משמעותי לעומת הסביבה הטרופית. שי שינה את הידע הבסיסי לגבי אידוי ומאזן החום במפרץ אילת. מתוך המדידות הישירות הוא מצא שקצב האידוי השנתי גבוה פי 2 מהערכות הקודמות, וכי עיקר האידוי מתרחש בקיץ ופחות בחורף. שי כבר פרסם ממחקרו מאמר מדעי בכתב עת מוביל, ומאמר נוסף נמצא בשלבי כתיבה סופיים. שי הוכיח שהוא סטודנט מצטיין בלימודים ובמחקר, הוא בעל מוטיבציה, סקרנות, יצירתיות, חשיבה עמוקה ובסיס מדעי רחב. לאור כל האמור, בחרה הוועדה להעניק לתלמיד שי אביר את הפרס שרגא דיקר לשנת תשפ"ג, ולראיה באו על החתום חברי הוועדה ארי מטמון וסיימון עמנואל. עכשיו אני אבקש משי אביר לבוא לקבל את הפרס. מה? שנייה. כן, בהחלט. רגע, תשאר. רגע, שנייה.
אז תודה רבה קודם כל על המילים החמות. גבירותיי ורבותיי, חברי סגל נכבדים וסטודנטים עמיתים, ראשית ברצוני להודות למשפחת ארנון ודיקר, משפחות החללים מנחם שרגא ותיאודור דיקר, זיכרונם לברכה, על תרומתכם ארוכת השנים עבור מחקר מדעי כדור הארץ. בחרתם להנציח את יקירכם בקידום מחקר מדעי כדור הארץ בישראל, נושא שהיה קרוב לליבם ולבכם, אז תודה רבה. למנחים שלי, הפרופסורים נדב לנסקי, אפרת מורין, המיש מגרן, תודה על החופש ועל המרחב להביע את קולי, ובפרט על ההנחיה הקשובה והביקורת והמימון. לשותפים למחקר, דוקטור יונתן שקד ופרופסור חזי גילדור, על תרומתכם למחקר, לשאר סגל המכון האדמיניסטרטיבי על פתרון כל בעיה, לחוקרים, על הקורסים שהזכירו לי גם להסתכל הצידה מתחומי המחקר שלי ולהרחיב את תחומי הידע ואבני הבניין, לעובדי המכון הגיאולוגי והמכון הבין-אוניברסיטאי באילת, תודה עבור העזרה הבלתי מתפשרת בעבודת השדה ופתרון הבעיות, לחברים במכון על הזמנים בין ומחוץ ללמידה, ולחברי קבוצות המחקר עליהם אני משתייך, על הדיונים הערים, הביקורת והעידוד, ושוב תודה למשפחת ארנון ודיקר על תמיכתכם במפעל זה. אלו הרבה תודות ללא מעט אנשים שעזרו לי ללכת את צעדי הראשונים בעולם האקדמיה, ופה ושם גם להגיע להישגים, אז תודה.
אוקיי, עכשיו אנחנו נעבור לחלק של הסמינר המכוני, אז צחי.
אחלה, תודה. אז רק פרסומת קצרה, ביום שני, ב-10:30 בכיתה 126, אנחנו הולכים לעשות סשן שחלק מהסטודנטים שלנו לתואר שני, שנה שנייה, הולכים להציג את המחקרים שלהם. אז אם אתם רוצים לשמוע את המחקר של שי אביר ועוד סטודנטים, אתם מוזמנים להגיע. ועכשיו יש את הסמינר של יניב דרבסי, את סמינר הדוקטורט, התלבטנו מי יציג אותו, אמוץ או אני, ובגלל שלאמוץ יש יותר מדי מה להגיד ולי יש מעט מה להגיד, אנחנו כבר אחרי הטקס, אז קבל את יניב, אני אגיד מעט. יניב עשה פה תואר ראשון, שני ושלישי, וזהו.
שומעים אותי בסוף? לא נראה לי. שומעים? Okay, so thank you Tzachi for the introduction, and today I will talk about three main chapters of my PhD. The main issue is integrating seismic for the shallow subsurface, and the three main chapters will be site amplification, uncertainties, and one geo-engineering, which will be a case study. All my work was done under the supervision of Amotz Agnon and a lot of help from John Hall. So the agenda for today will be a general background and motivation, and then we will dive into the three main chapters: better attenuation relation for the Dead Sea region, comparison between the different seismic techniques, and one environment study case. So a general background about seismology. What is ground motion? So ground motion refers to the movement of Earth's surface during an earthquake or any other event. Okay? It can be traffic, airplanes, walking people, it can be everything that we can record. How can we record these kind of things? We can measure it by the acceleration over the time, or velocity over the time, or the displacement over the time. So this ground motion is controlled by three main factors. The first one is the source, or what are the property of the source, which kind of fault, what is the directivity of the waves. The second one is the source distance. So what is the distance between the epicenter location and the site himself, where we are trying to measure the ground motion. And the third one is the near surface geology or site effect, which you can see here, this building, which is the end where we are feeling the ground motion. So this site amplification can be attributed from different aspects. We can talk about Bayesian effects, focusing effects, topographic, or what is more relevant for us today is soft soils over hard bedrock. Another important thing to understand before we will dive into the chapters is what is attenuation relation. So what you're seeing here are a lot of dots which describes the seismic intensity as a function from the epicentral location. Okay? Then we are trying to fit kind of curve that will fit all these dots. And you can see that most of the time this curve fitting is not so well. This is a good example for site amplification, and maybe the most famous one of Mexico City. You can see here in the left map the epicentral location of this event, and all the yellow, green, brownish colors are the waves or the seismic intensity or the peak ground acceleration. And you can see that all this acceleration, all these waves are spreading spherically. You have a kind of a semicircle here, and then they all attenuated. But look what happened at the city of Mexico City. We can see here a significant amount of peak ground acceleration. If we will look at this schematic section, we can see that the epicentral location is far about 400 kilometers from the city of Mexico City. Okay? The city of Mexico City is sitting over soft layers over hard bedrock, which you can see this section is the soft sediments. 2 accelerometers were measured, these accelegrams that you're seeing here, and you can see that the peak ground acceleration of the site which sits over a bedrock recorded much lower accelerations than the one which sitting over the soft layers. Okay? This amplitude comparison to this amplitude. So this is a perfect example for site effect. So now how can we measure or connect this site effect or ground motion into the physics? So the basic idea is that stiffness of material is defined as a measure of resistance to deformation and related to 3 main modulus, okay? The Young modulus, the shear modulus, and the bulk modulus. Without getting too much in details about these 3, I will just say that the 2 most important are the shear modulus and the Young modulus. The reason is because we don't have any difference in volume while we have an earthquake. So the shear wave velocity is this, you can see in this equation. This is G, the shear modulus, and you can see that it depends only on the density and the shear wave velocity. So this is why the shear wave, the Vs, is used as direct indicator of the material stiffness. Now, how can we measure this shear wave velocity, which we see that is important to our study? I will show you 3 different types of measurements in order to retrieve this shear wave velocity profile. The first one, and maybe the most common today, is the multi-analysis of surface waves, or the MASW, which suggested by Park et al. At 1998. The basic idea behind it is that we are using surface waves, or the unique property of surface waves, which is the dispersion. Okay? What is the dispersion of surface waves? You can see in this illustration, we have a linear array of geophones, and here we have an activated source. So the first geophone who's sitting here, which is the nearest one to the source, will record for amount of time the parcel of all the wavelength. Okay, so this is this section. And the last geophone will also record this event, but now the time it records the same event is longer. So this time differences between the first geophone and the last geophone is the dispersion. And what it means for us, that each frequency has its own velocity. So if we will transform the time distance from the time distance domain into the spectrum domain, we can see that for each frequency we can pick different phase velocity. This is a normalized amplitude, so the red colors are more energy. And you can see that, again, for each frequency we can define a different phase velocity. After we're picking our dots, we can invert the data and we can receive this inversion profile. How can we do that? Each frequency penetrates differently to the subsurface. So the lower the frequency, the deeper the data. Two other methods that I used in my PhD. The first one is the refraction microthermal, or the REMI, suggested by Louis back in 2001. It's the same concept as the MSW. Instead of using an activate source, we're using passive sources. Second method is the extended autocorrelation, or ESAC. This method is a bit more complicated because we are using 2D arrays, such as this kind of things. And we're also recording just passive noises. And then by the Bessel function and the coherency, we are trying to see what is the difference between the phases of each of the wavelengths between the geophones. Okay? The end of all these methods is to retrieve this kind of dispersion image. And again, this is a normalized amplitude. And we're trying to pick the best fit for this image and invert to the shear wave profile with the depth. The last method that I use, which is a bit different from the surface wave method that we just saw, is the HVSR, or the horizontal to vertical spectral ratio. This method uses a single broadband 3-component seismometer that measures seismic noise in 3 orthogonal directions. What we're doing with this data is taking the spectra of the horizontal geophone, seismometer, and then we are divided by the vertical component, and we can receive this kind of figures. This kind of figure are showing us what is the peak frequency, which is the amplification from the boundary at the subsurface. Okay? So for instance, this figure we have amplification around 2 Hz. Okay? What we can do with that? So with this basic equation, we can see that if we have the fundamental frequency, which we just pick from here, and we can estimate the shear wave velocity, we can calculate what is the depth to this layer. Okay? And we can do it in the reverse way. If we know the fundamental frequency and we know what is the depth to this layer, we can understand or calculate what is the shear wave velocity. To summarize all the methods I used, I put here this table, and I will just mention that for the first method I talked about, the MSW, we can acquire data for 3 different types of components. We can acquire data for the vertical component of Rayleigh waves and also for the radial component of Rayleigh waves, and we can also acquire data for the transverse component of lav waves. Okay? This is 3 different types of data sets we can acquire. The sensors I used are all come from the Yaniv Center for Geoinformatics, and this is a good time to say thanks to John, who donated most of the equipment. And the sensors that we used are most of the time 5 or 8 kilogram sledgehammer. And during the research, we found that maybe we need something heavier or something that generates different frequencies. So we designed this mechanical source together with the team of Amos Shiran and this guy Hanan. And you can see here the mechanical source acting as a P wave generator and S wave generator. This is the first prototype. Now it looks better than this. So now that we know everything, we can start talk about the 3 main chapters. And I will start with this section of better attenuation for the Dead Sea region. This paper published about 4 years ago. And the main idea here was to taking historical data and working with shear waves, with modern shear wave velocity analysis, and came up with a new equation relation or attenuation relation. So I'm going back to this graph, which is the seismic intensity as the function of the epicentral location. This graph I took from Ron Avni's PhD. And you can see, again, how significantly are the dots. The R square of this curve is 0.26, which is not high. This event is from the 1927 earthquake event, okay? The event of Jericho, which you can see this picture. So the first thing I did is to take Haf and Avni data from 2011. And again, it's the same dots with the same intensity. And I plot the attenuation equation together with a boundary of 60%. What is the meaning of this boundary? It simply says that all the blue dots are 60% of the data. All the yellow dots are 40% of the data, and they are outside of this boundary, and they are far away from the expectation of the attenuation relation. So these yellow dots are more relevant to my research to try to understand if the geology, the near surface, is influenced on them, and this is the why they are far away from the expectation. So here you can see all the 21 sites that I measured. For several of them, I measured at 2 sub-sites. And to the left, you can see the different optional epicenter locations. So after the 1927 event, the first epicenter location was Damia Breach, and it was by the International Seismology Summary. And then you can see that we had several other. We decided to take Almog as the best location, which Zohar and Marco in 2012 relocated by a very complicated model. So in order to define the final equation, I used 2 different equations. The first one came from Haf and Avni, which you can see it here in red. And all the C coefficients that you see in here came from their paper. Their equation depended only on the magnitude and the distance, okay, these 2. The second term, which I want to use with modern shear wave velocity analysis, is this term, which came from Boer et al. 1997. This is the full equation, and I just took this relevant part, which depends on the shear wave velocity. And in order to calculate what is the BV and the VA, I use the least square fitting to get my numbers, which is here in the final equation. How the model works, simply I took what is the difference between the observation intensity and the predicted intensity, and where is the lower, the better attenuation equation. How this equation looks on graph. So again, you can see here the attenuation relation with the 60% boundary. You can see the yellow dot, which are the observed one. And in black, the dots and the uncertainties, you can see how the new equation corrected these dots. So this is the effect of the shear waves or the local geology, and you can see that for a lot of the dots now, they are inside this 60% boundary. We still have some problem, nothing is perfect, and we can explain this, but we will not go too much in details about this section. So the outcome of this chapter is mainly a new attenuation relation, which including the VS term, but 2 main thoughts I had about this research. The first one, I used only the MSW method, which is just one method without too much uncertainties that can I say something about it. The second one is the lateral changes, and in order to emphasize this, I put this graph, which you can see 7 different sites, which for each of them I had 2 locations where I acquired the shear wave velocity. So for instance, this site of Moza, I acquired data at 2 different sites, which are a difference of distance of about 500 meters. And you can see that the results are a difference of more than 40%, which is significant. This is lead me directly to the next chapter, which is quantifying uncertainties and using better techniques, and more than that, using more techniques. So this paper published 2 years ago, and I measured with a lot of techniques at 6 different sites. The main motivation was to quantify uncertainties, maybe understand what is the best method or which of the methods have less uncertainties. So here you can see the 6 sites. Here you can locate them on map. And the sites are באר טוביה, בית שאן, קיסריה, הוד השרון, מגדל העמק, and רמלה. For each of them, I add at least one geological borehole. And the acquisition for each of the sites was as follows. You can see here the shape of L, which each triangle is a geophone, and these red bumps are where we activated the source. And for each of these sites, we can acquired 4 different type of data sets. The first 3 are the components for the MSW, which I described before, and 1 data set, a passive data set for the REMI. So 4 data sets from this line and 4 data sets from this line. And for all this array, we can collect data for the ISAC method. So in total, we are talking about 9 different data sets for the same sites. Unfortunately, we didn't succeed to make this model or acquisition in each of the sites, just in terms of logistics. We didn't have enough space or things like that. Don't be afraid from this slide. I will explain everything in the next few slides. This is basically how the results looks for each of the sites. So this is just one example from the 6. So here you can see in the first column the raw data of the different methods. Here we have the MSW. Here the raw result for the REMI and the ISAC. You can see clearly the difference between the active methods and the passive ones. In the middle column, you can see the dispersion image, which is the transformation from the time domain into the frequency domain. And at the end, here you can see also the experimental peaks and the theoretical ones for each of the graphs. And at the end, you can see the results after the inversion, where we can see the shear wave profile. This is the result for the HVSR method. You can see here the amplitude frequencies. And here is the density spectrum for each of the component. Okay, this is the vertical one, and this is the 2 horizontal ones. And here we can see the azimuthal HVSR, which says what is the HVSR, which we saw before that, this curve, for each azimuth. So in order to quantify the uncertainties, I use this coefficient of variance, or the COV, as I will call it from now on. And the COV is the standard deviation divided by the mean. The important thing to understand here is that the lower the COV, the lower the uncertainties. Okay? I will say it again because this is the most important here. The lower the COV, the lower the uncertainties. So we can see here all the dispersion curve results, which came from 9 different data sets, also together with the average, this black tick curve. And when we are looking at the uncertainties or the curve, you can see that it ranges between 5.5, something like that, up to 8%. And the average is about 6. When we are looking after the inversion process over the shear wave profiles, we can see that the curves are much higher. Okay? We can see that the average curve is more than double than the one that we saw here for the dispersion curves. More than that, when we are looking at depths of about 15 meters, we can see that we have sections with a curve with more than 20%, which is a significant uncertainty. In order to show you all the results of these sites in 2 plots, you can see firstly this one, which is the average shear wave velocity divided by the average of all the results. So number 1 here indicates the average. So for instance, if we were looking at the ISAC method or the ZVF of the short line, we can see that their results are almost exactly as the average of all the other 9. Okay? And if we will look at each of the methods, what is the variability or what is the uncertainty of each method, we can see that, for instance, the ISAC method have about 4% curve. This all results of the all HVSR. And again, I will just show you one example of Be'er Tuvia. you can see here the HVSR over time, which these tiny curves all came from a short window. Okay, I take all the 1 hour record and divide it for several windows, and from each window I calculate the spectrum, and the main thick blue curve is the average of all of them. Here is the HVSR directivity, and at the end you have the amplitude spectra. The important thing here from all these three graphs is to try to understand if we are talking about a real site effect or real geology, or we're talking about something that is artificial, so something like this kind of peaks which are non-geology. In order to conclude this chapter, I plotted two graphs. The first one is the average shear velocity of each of the methods at each of the site, divided by the all methods. So you can see that for Bet Shean, we have ranges from 7%, some up to 7%, and for Migdal HaEmek, we have up to 16%. Okay? So we have significant uncertainty for this site, and the uncertainty of the individual method can lead to misinterpretation of the shallow subsurface, because 60% may lead to significant errors. The second plot that you see here is the whole 33 sites that I measured, and what is most significantly you can see here is that the average of all of them, and again you can see here the different methods, for each of them the average is about 8%. Okay, so it doesn't matter which type of test I'm using, the average curve is about 8%. So there is no correlation between the test type and the curve, and while there is no preferred method, it is still advisable to use several methods for data acquisition. Two main final remarks to this section. The average index, the shear wave velocity for a certain amount of depth, is less sensitive to uncertainties, and it is therefore much more robust. Secondly, the study aligns with comparable shear wave studies and falls within the acceptable uncertainties in the result. This suggests that such tests are also applicable in industrial zones where the signal process may be affected by noise. Again, all these sites were required at industrial zones when we have traffic, machines, and a lot of things. And we still succeed to retrieve the shear wave velocity with the different methods. This leads me directly to one case study where I will show you how we use the different techniques and evaluate the different uncertainties. The main motivation here was to estimate what is the landfill thickness, and when I'm talking about landfill, I'm talking about waste deposit, unabandoned waste deposit, where we just want to know what is the thickness of this thing. Okay, so the geometry of this landfill is pretty clear. You can see it here. We had some rocky limestone here, and alluvium, and some agricultural area at this site. And the acquisition that we used here was with the REMI, ISAC, HVSR, and the classical approaches of seismic reflection and seismic refraction. You can see, again, this is the border of the landfill, and this is the reflection and refraction seismic lines, and also together with the HVSR, ISAC, and REMI data sets. So the results of the seismic reflection clearly shows us a boundary at about 15 meters. And again, when I'm saying boundary right now, I'm talking about the base of this landfill. Okay, what is the depth between the surface to the base of this waste deposits? And the second line shows us pretty much the same picture of border at around 15 meters. The refraction line shows us a shallower boundary. So you can see between 11 meters to 12 meters. And all the surface waves methods show us pretty much the same numbers. You can see from the ISAC method, we're having a boundary at about 10 meters. I will just say that you can see here the velocity, the numbers of the velocity. Now we are talking about lower velocity. Okay, so here the boundary is having 350 meters per second, which is shear wave velocity. And here we talked about P wave velocity, which have higher velocities. So this is the first one. The Remy method of the same line shows us a boundary about 12 meters. And for the next line, line 4, the ISAC method, again, about 11 or 12 meters. And the last one from the surface waves, something around 10 meters. The last method that I used in this area was the HVSR. The things here are more complicated. And you can see that for line 3, we can see or say something about amplification around 4 Hertz for mostly all of the data sets. For each of the line, I had 12 different data sets. So all of them are converged to this area, besides just one. For line 4, the things are much more complicated, and it's hard to say where exactly is the amplification, if there is any amplification. But still, we can use this data together or integrate it together with all the other information. So I will just remind you that the HVSR by itself doesn't help us a lot. We need to use this equation in order to calculate what is the depth to the base of the landfill. So in order to estimate what is the shear wave velocity, I took the average of the first 10 meters from the surface waves method. So the calculated is about 130 meters per second, plus minus 31. And when we are putting in this equation, we are receiving something like 8 meters plus minus 2, which is about 25% error. This is significant. In order to see all the pictures together, all the methods in one plot, I plotted this graph. You can see in blue the seismic reflection together with its uncertainties. In green, you can see the surface waves and the uncertainties. And in black, you can see the HVSR with more significant uncertainties. You can see that for a first approximation, we have pretty nice picture where all the data converge to a nice boundary at about 9 or 10 meters. And if we are taking into consideration also the uncertainties, we can talk about a boundary at about 8 to 12 meters. So again, for first approximation without any borrow or without any other information, this is a good indication. For the second line, again, you can see that most of the methods converge pretty well. Again, the dots of the HVSR are more problematic. I will remind you that we use the equation of the dividing by 4, this one. So if I will take different number for the shear wave velocity, I will get different numbers for the depth. So to conclude this chapter, the results of all methods correlate comparably well with each other. The HVSR method should be considered with caution, and uncertainties are significant. By combining several geophysical methods, which are non-destructive, environmentally friendly, and relatively low cost, the reliability of the results may increase and yield a more accurate solution. Lastly, the approach test can better assess uncertainties and allow an efficient solution for environmental or engineering process. Now, in order to summarize all these 6 years of PhD or these 3 main chapters, I asked myself, what is the main question I want to ask myself? And I came up with, what is the best way to evaluate the shear wave velocity? So today we have ChatGPT, which maybe is the new God or something like that for the youngers. And I asked him this question. So the answer was, the choice of method depends on various factors such as the site condition, accessibility, accuracy requirement, and budget. And secondly, it is often recommended to use combination of methods to obtain a more comprehensive understanding of the subsurface and improve the reliability of the results. So for those of you who were focusing during the lecture, this is the same conclusion that I took. So I think ChatGPT took this conclusion for me, but I'm not sure about it. And This is a good time to say thanks to a lot of people. First of all, to the researchers and the students of the Yaniv Center of Geoinformatics, especially to Usnat, who helps a lot at the field, and also to Benny Medvedev, who were the first one to receive me to the academy, and also to the committee, Ron Shar and Goni, and to three main people. This guy here, who's sitting here, Eli Ram, who helped me a lot, who volunteered and went me to the field all the time. Thank you, Eli. Secondly, this guy sitting here, John Hall, who donated most of the equipment, helped me a lot with bureaucracy, writing in English, talking in English, everything. And lastly, this professor, Amos Agnon, who was like, I don't know, my mentor, my father, my grandfather, everything. Thank you very much. Now you can shoot me.
Nobody's shooting. Thank you. Questions?
בסדר, אפשר ללכת. Yes.
You said that in these case studies that you measured the depth velocity profile, you had boreholes?
I didn't have any boreholes.
Any boreholes?
Any boreholes. I want to have them, but I don't have them.
When you compare the different methods, the RPF, which I'm not sure what are the...
What's the meaning of them? So the ZVF is the vertical component of Rayleigh wave. The RVF is the radial of the vertical of the Rayleigh waves, and the THF is the transverse of love waves.
Okay, so RPF seems to be consistently higher than the other methods. It's always above the average.
Well,
I wanted to ask you if you have an idea why it's always higher.
You're talking about this section? So you're saying that the RVF or the rectangles are higher. So if you will, you can see that the lower numbers beneath the one are also uncertainties. So all these dots, these diamonds, which are the Remy, are also with higher significant, higher errors. So this one is about let's say 40%, okay? And this one is almost 50%. Okay, so these are also with higher uncertainties. So you don't have any preferable uncertainties for each of the sites.
But I'm asking why are is there a reason why the RPFs, I mean, I'm asking you if you have an idea why the RPFs are always on the high side of the...
No, but I'm not agree about it. That's what I'm saying, because you can see that all the RVF, which is here, the uncertainty of them is about 5%. Okay, 5 something, 5, and this is one is 9. Okay, and when I'm looking at these diamonds, which are the THF, we are talking about 10%, 8%, 7%. So they are almost the same. So I don't see any correlation between the uncertainties and the type of and the method. In this research, maybe in other research it will be differently.
No, I have. So you did the inversion only for the first mode, only for the fundamental of the different?
No. I didn't talk about the different modes in the inversion process, where I had some, I will try to show that. I had several dispersion images with higher modes. When I had them, I tried to model them with the higher modes, which is much more accurate. Yes. Yes.
Did you also do the different, like the Rayleigh waves and love waves together?
No, everything was separately.
Okay, so doing it together may be more stable.
For sure.
Okay,
Yes.
and the Remy method?
There?
You did the middle one.
Tell me.
Yeah, do you do cross correlations or you just calculate phase velocities on
Phase velocity over the RME, and the reason that I picked the lower boundary because we're using passive data and I don't know where is the source.
Yeah. Because if you use it in high frequencies, the source may be located on
Yes.
one side of the array, and then you get apparent velocities instead of the real velocities, which may be bias.
Yes.
Okay, so you're
Yes.
So if you have additional time and no financial limits, what could you do more to strengthen your observations? And then
Acquiring more data.
just
More sites, more data. You know, we are talking here about 6 sites, 33 measurements, which is maybe for a few of you it looks a lot, but it's nothing. I want to you know, when you're doing statistics, you want 100 data sets, thousands of data sets. It's not enough.